In early 1944, Dayton, Ohio, a test pilot steadied his hand on the throttle of a P-51B Mustang as he pushed past the standard war emergency power setting. The engine roared and the boost pressure climbed to 75 inches of mercury, powered by a new experimental fuel known as Grade 150. The airspeed indicator raced past speeds that previously marked the peak of what Allied fighters had achieved. At 25,000 feet, the Mustang was accelerating to 448 mph. On the ground, the test engineers exchanged looks as the pilot's report came through on the radio. This was not just another small upgrade. It was a breakthrough that would reshape the war. This was a chemical advantage so significant that it would nullify every assumption the Luftwaffe held about American fighter performance. The balance of power in the skies over Europe was about to shift, and it wasn't due to a new aircraft design or a brilliant tactical move, but because of a fuel that allowed existing fighters to perform in ways that defied German expectations. What the Luftwaffe didn't know was that American and British fuel chemists had achieved something that Germany's synthetic fuel program could never replicate. While German fighters were stuck using B4 fuel, rated at 91 octane, and their best, C3 fuel barely reaching the equivalent of Allied 130 grade fuel, American refineries were producing aviation gasoline with a 150 grade performance rating. The implications of this were enormous. A P-51 Mustang running on 130 grade fuel could reach 437 mph at 25,000 feet. With the new 150 grade fuel, the same aircraft could exceed 448 mph to German pilots who had learned to respect the Mustangs. Range and high-altitude performance were about to face a new, insurmountable challenge. The Messerschmitt Bf-109G, the Luftwaffe's frontline fighter in early 1944, had a top speed of 400 mph at altitude. The Focke-Wulf 190A could reach 408 mph under optimal conditions, but against Mustangs using 150 grade fuel, German fighters were at a fundamental disadvantage, one that no amount of pilot skill or tactical brilliance could overcome. The origins of this advantage lay not in wartime innovations, but in the peacetime efforts of petroleum chemists, who understood that octane ratings measured how much a fuel-air mixture could be compressed before spontaneously detonating. Higher compression ratios meant more power from the same engine, a crucial breakthrough that gave the Allies a decisive edge. Each combustion cycle required more power, leading to faster aircraft and higher operational ceilings. While the science was clear, the engineering needed to produce high-octane aviation fuel at an industrial scale was incredibly complex. In 1940, as the war raged in Europe, American aviation fuel production was based on 87-octane gasoline. This was sufficient for commercial aviation and early military trainers, but inadequate for high-performance combat aircraft. The British, desperate to gain any advantage over the Luftwaffe's superior numbers, collaborated with American oil companies to create a 100-octane fuel, which became available just in time for the Battle of Britain. The difference was immediately noticeable. British Spitfires and Hurricanes using 100-octane fuel gained 30 to 40 mph more speed at altitude, and their climb rates increased by 500 to 1,000 feet per minute. German pilots, who had enjoyed performance advantages with their 91 to 100-octane fuel, suddenly found themselves on equal footing. The development of 130 grade fuel marked another leap forward. This fuel, with a performance number of 130 on rich mixture settings, became the backbone of Allied air power in 1943. It powered the Merlin engines in both Spitfires and Mustangs, the Allison engines in P-38 Lightnings, and the massive Pratt & Whitney R-2800 radials in P-47 Thunderbolts. Production of high-octane fuel scaled rapidly under the leadership of General James Doolittle, who had spent the 1930s convincing both the military and oil companies to invest in the development of high-octane fuel. By 1943, 17 Allied refineries were producing high-octane aviation gasoline using the catalytic cracking process perfected by French engineer Eugene Houdry. American refineries alone were producing millions of gallons each month, enough to fuel the massive bomber campaigns against Germany and the growing fighter forces that protected those bombers. In contrast, Germany's fuel production was hindered by its reliance on synthetic fuel derived from coal. The laborious process of converting coal into aviation gasoline was technically sound, but slow and resource-intensive. Even at peak production, Germany could only produce a fraction of the high-octane fuel that flowed from American refineries. Most German fighters used B4 fuel, rated at approximately 91 octane on the lean mixture scale. Their premium C3 fuel, used mainly in BMW 801-powered Focke-Wulf 190s and select Messerschmitt variants, was roughly equivalent to Allied 130-grade fuel, but was produced in much smaller quantities. By 1944, about two-thirds of Germany's aviation fuel production was C3 grade, still only a small fraction of what the Allies were producing. Understanding fuel performance requires understanding the basics of internal combustion engines. Octane ratings measure detonation resistance. When a piston compresses the air-fuel mixture during the compression stroke, temperature and pressure rise dramatically. If the fuel ignites prematurely before the spark plug fires, detonation occurs, causing an uncontrolled explosion rather than a controlled burn. This creates shockwaves that can damage or destroy engine components. Higher octane ratings mean the fuel can withstand higher compression without detonating. Octane ratings cannot exceed 100 because 100 octane is the detonation resistance equivalent to pure iso-octane, the reference standard. Performance numbers measure how much better a fuel can perform beyond pure iso-octane. A fuel with a performance number of 150 can withstand 50% more compression than pure iso-octane before detonating. Creating such fuel required adding anti-knock compounds, primarily tetraethyl lead, and carefully blending aromatic hydrocarbons like toluene and xylene with the base gasoline. British fuel chemists at the Royal Aircraft Establishment tested various blends in 1942 and 1943 to find the best combination of anti-knock performance, energy content, and manufacturing feasibility. American researchers at Wright Field conducted parallel studies, sharing data with the British. By early 1943, both nations had produced experimental batches of what they called 150-grade fuel. While the name was somewhat misleading, it suggested an octane rating of 150, which was chemically impossible. It actually referred to a fuel with a performance number of 150 on the rich mixture scale and 100 octane performance on the lean mixture scale. This fuel, dyed purple for easy identification, underwent extensive testing through 1943, with results exceeding expectations. Merlin engines running on 150-grade fuel could sustain manifold pressure readings of 75 inches of mercury, compared to 67 inches on 130-grade fuel, which translated directly into increased horsepower. A Packard Merlin V1650-7 engine, which powered the P-51D Mustang, generated 490 horsepower at standard military power on 130-grade fuel. When running on 150-grade fuel at war emergency power settings, the same engine produced 1,720 horsepower. In the P-51B, with its V1653 Merlin variant, pushing output to approximately 1,600 horsepower. Flight testing at Wright Field confirmed the significant performance improvements. The performance gains were substantial across all flight regimes. Maximum speed increased by about 25 to 30 mph at altitude, while climb rates improved by several hundred feet per minute. Most importantly, these improvements were achieved without modifying the aircraft itself. The same Mustang, flown one day on 130 grade fuel and the next on 150 grade fuel, became measurably faster and more capable simply due to the fuel it consumed. The decision to introduce 150 grade fuel to operational fighter squadrons was made in early 1944 with careful timing. The 8th Air Force, based in England and conducting daylight bombing raids deep into Germany, was suffering unsustainable losses. Despite the arrival of the first P-51 Mustangs in December 1943, German fighters were still inflicting heavy casualties on American bombers. What American planners needed was not just a long-range escort fighter, but one so fast that German interceptors couldn't easily escape or refuse combat. In May 1944, the first operational deliveries of 150 grade fuel arrived in England. Distribution was carefully controlled, with not every fighter group receiving the new fuel immediately. The 8th Air Force began with select squadrons to manage supply logistics and evaluate combat performance. The British Royal Air Force, which had been involved in early testing, also began equipping fighter squadrons with the new fuel, prioritizing those tasked with high-speed interception missions, particularly against German V-1 flying bombs terrorizing London by June 1944. The V-1 flew at around 400 mph at low altitude, and intercepting it required fighter aircraft capable of matching or exceeding that speed at low levels, where air density reduced aircraft performance. Hawker Tempests and Spitfire 14s could barely catch the V-1s, and Mustangs running on standard fuel were only marginally effective. However, Mustangs running on 150 grade fuel had enough speed margin to reliably intercept. On June 18, 1944, Major R.E. Turner of the 356th Fighter Squadron destroyed a V-1 by tipping its wing using his P-51's wingtip, a technique repeated 16 more times during the campaign. The first widespread combat use of 150 grade fuel by American P-51 pilots occurred in June 1944, coinciding with the Normandy invasion. Fighter groups of the 8th Air Force, tasked with achieving air superiority over the invasion beaches, flew combat air patrols and bomber escorts using the new fuel. German fighter pilots began reporting encounters with Mustangs that performed beyond anything they had previously experienced. Luftwaffe intelligence officers collected pilot reports describing American fighters that couldn't be caught in any flight regime, accelerated away from German interceptors with ease, and seemed to have power reserves that defied explanation. Initially, these reports were dismissed as pilot error or exaggeration, as German pilots were considered tired, outnumbered, and suffering heavy losses. Their accounts of superior American fighter performance were seen as the result of stress and fatigue. This assessment, however, was wrong, and the truth would not be clear until after the war. A Luftwaffe ace with 275 victories, mostly on the Eastern Front, flew combat missions against American fighters over Germany in 1944. After the war, in interviews from the 1970s and 1980s, he recounted his encounters with late-war Mustangs. He was shocked by their speed, climb capability, and high-altitude performance. What he and other German pilots didn't realize at the time was that they were facing an aircraft whose performance had been chemically enhanced beyond its original design specifications, operating at power settings the Mustang engineers had never envisioned. The Rolls-Royce Merlin engine, produced under license by Packard, was designed with careful attention to thermal limits, bearing loads and detonation margins. Running an engine at higher boost pressures pushed all these parameters to their limits. What made 150 grade fuel revolutionary was that it allowed engines to operate at these extreme settings without the catastrophic detonation that would have destroyed engines using lower grade fuels at the same boost pressures. The chemistry behind this capability involved a complex interaction of fuel molecules, air molecules, heat, and pressure inside the combustion chamber. Tetraethyl lead, the primary anti-knock additive, interfered with chemical chain reactions that would otherwise lead to spontaneous ignition. But there were trade-offs. Tetraethyl lead was toxic, requiring careful handling by ground crews, and left deposits on spark plugs, valves, and cylinder walls, increasing maintenance needs. The high lead content of 150 grade fuel accelerated these maintenance issues. Fighter groups using the new fuel experienced more frequent spark plug fouling and increased cylinder wear. American maintenance procedures adapted quickly. Spark plug replacement intervals were shortened, cylinder inspections became more frequent, and engine overhaul schedules were adjusted. The performance gains were deemed worth the increased maintenance burden. For pilots, transitioning to 150 grade fuel required new operating procedures. Manifold pressure limits were raised, and pilots had to be cautious not to overboost engines, particularly at low altitudes where air density was highest. Most importantly, pilots had to learn to manage fuel consumption. 150 grade fuel provided more power, but running at maximum boost consumed fuel quickly. Escort missions to Berlin and back already pushed the Mustang's range to its limits, and using the new fuel's full capabilities meant careful fuel management. Knowing when to use maximum power and when to throttle back for cruising efficiency, combat reports from the summer and fall of 1944 documented a dramatic transformation. 8th Air Force fighter groups equipped with the new fuel reported higher victory-to-loss ratios and better success in intercepting German fighters attacking bomber formations. German fighters, which had once been able to make fast, slashing attacks and then escape, now found themselves unable to outrun pursuing Mustangs. On August 6, 1944, Lieutenant Hollis Bud Nylin of the 357th Fighter Group, flying as part of Operation Frantic missions to Soviet air bases, encountered German fighters over Eastern Europe. Flying his P-51D Hellsbells and using 150 grade fuel, Nylin engaged a Messerschmitt Bf-109, flown by G. Shack. In the ensuing combat, Nylin's speed advantage proved decisive, allowing him to close rapidly on Shack's aircraft and fire a burst that damaged the German fighter's cooling system. Low on fuel and ammunition, Nylin broke off the pursuit, waved to the German pilot, and returned to escort duties. Shack belly-landed his crippled aircraft near German lines. For 40 years, Shack wondered why Nylin hadn't finished him off, never realizing that Nylin had believed he had only damaged the aircraft. Later, historians connected the two pilots and arranged a meeting in Germany, where Shack acknowledged that the American Mustang's performance exceeded anything he had ever encountered. The speed with which Nylin closed and the power reserves shown during the engagement were unlike anything he had experienced in combat with American fighters. The psychological effect on Luftwaffe pilots was profound. Already outnumbered and facing superior Allied numbers, they now confronted American fighters that seemed to have unlimited performance margins. Their tactical options became severely limited. The Luftwaffe could attempt mass attacks, hoping sheer numbers would overwhelm the escorts. They could refuse combat entirely, saving their aircraft and pilots. Or they could engage and likely be shot down by Mustangs that were faster, more maneuverable, and flown by American pilots who were growing increasingly confident and aggressive. Reich Marshal Hermann Göring, commander of the Luftwaffe, famously remarked upon seeing P-51 Mustangs over Berlin that he knew the war was lost. His statement reflected the Luftwaffe's strategic dilemma. The Mustang's long range meant no part of Germany was safe from American daylight bombing. The introduction of superior fuel in mid-1944 deepened this crisis. Luftwaffe technical intelligence eventually obtained samples of Allied 150-grade fuel from captured drop tanks or crashed aircraft. German fuel chemists analyzed the samples and confirmed what Luftwaffe pilots had been reporting. The Americans had developed aviation gasoline with performance characteristics far beyond what German synthetic fuel plants could produce. Some German sources suggested that late-war C3 fuel approached the performance numbers of 150-grade fuel, but production was limited and quality was inconsistent. Allied bombing raids on German synthetic fuel plants, especially attacks on Leuna and other major facilities in May and June 1944, further hampered German fuel production. By late 1944, the Luftwaffe was rationing fuel. Fighter units received priority, but even they operated under strict constraints. Training for new pilots was severely cut back, and many German pilots entered operational units with minimal flying experience, unlike their American counterparts, who typically had several hundred hours of training before entering combat. Between January and May 1944, before the widespread introduction of 150-grade fuel, American bombers suffered loss rates of about 3 to 6% per mission, sustainable but painful losses. After the introduction of 150-grade fuel and achieving air superiority between June and December 1944, loss rates dropped to under 2% per mission. Fighter victories soared. American P-51 groups across the 8th, 9th, and 15th Air Forces claimed nearly 4,150 German aircraft destroyed in air-to-air combat from late 1943 to May 1945, with a significant portion of those victories coming after June 1944. The German pilot force, which had entered 1944 with substantial experience despite heavy losses on the Eastern Front, was systematically destroyed. By D-Day, June 6, 1944, only 2 Luftwaffe aircraft appeared over the Normandy beaches. While the Luftwaffe still had thousands of fighters, they lacked the fuel, trained pilots, and tactical flexibility to use them effectively. The technical specifications of 150-grade fuel are worth examining. Its lean mixture octane rating of 100 meant it resisted detonation, just like pure iso-octane when engines operated at cruising power settings. Its rich mixture performance number of 150 meant it could withstand 50% more compression than iso-octane when engines ran at maximum power. This combination allowed pilots to cruise efficiently for maximum range, then switch to rich mixtures. For combat, confident that the engine would not detonate even at extreme boost pressures. The handling of 150-grade fuel required special precautions due to its high tetraethyl lead content. Ground crews wore protective gear when fueling aircraft, and any spills were immediately cleaned up to prevent lead poisoning. Fuel trucks and storage tanks were clearly marked to prevent the accidental mixing of fuel grades. Despite these precautions, the safety record remained good, with industrial accidents being rare. The transition in operational squadrons required pilot training. Pilots received briefings on the new fuel's properties and updated engine operating procedures. Manifold pressure limits were raised, and operational guidelines specified when and how to use maximum power settings. Aircraft required no modifications. The engines, fuel systems, and all components were compatible with both fuel grades, which simplified logistics and operations. Production statistics tell the story of an industrial mobilization on a scale that Germany could not match. Between May 1944 and April 1945, the 8th Air Force consumed over 53 million gallons of 150-grade fuel. Allied production across all refineries likely exceeded 200 million gallons during operational use. Each gallon required refining infrastructure, chemical additives like tetraethyl lead, quality control testing, transportation to Europe, secure storage facilities, and distribution to dozens of airfields. American industrial capacity in 1944 was operating at levels that seemed almost miraculous. Factories produced bombers by the thousands, fighters by the tens of thousands. Shipyards launched Liberty ships faster than Germany could sink them. Oil refineries produced aviation gasoline in quantities that exceeded Germany's total fuel production across all grades. This success stemmed from decades of industrial development, vast natural resources, a protected homeland safe from enemy bombers, and a workforce that included millions of women working in factories to support the war effort. The Royal Air Force. used 150-grade fuel extensively in fighter operations over Europe. British squadrons flying Spitfire 14s, Tempest Veers, and Mustang 3Es and IVs received priority allocations of the new fuel. RAF pilots reported performance improvements similar to those experienced by American pilots. The Tempest, already one of the fastest piston-engine fighters in service, became even more formidable. Tempest squadrons achieved remarkable success with the new fuel. Between June and September 1944, RAF 150-wing Tempests achieved remarkable success against V-1 flying bombs, shooting down 638, with No. 3 Squadron alone claiming 305. Squadron leader Joseph Bry downed 59 V-1s. Belgian ace squadron leader Remy van Leeuwen destroyed 44, and wing commander Roland Beaumont brought down 31. The next most successful interceptors were the Mosquito with 623 kills, the Spitfire 14 with 303, and the Mustang with 232. The performance margin proved advantageous in every role. The combat effectiveness of 150-grade fuel was repeatedly demonstrated through late 1944 and early 1945. Fighter groups equipped with the new fuel reported higher victory claims and lower losses. By March 1945, virtually every P-51 unit was using the new fuel. Combat reports from this period showed overwhelmingly one-sided results. German fighters rarely challenged Allied formations effectively, and when they did engage, they usually suffered heavy losses. By April 1945, missions over Germany often encountered no aerial opposition. The Luftwaffe had been decimated by attrition, fuel shortages, and the systematic elimination of experienced pilots who could not be replaced. On May 8, 1945, Germany surrendered, and the air war over Europe ended with absolute Allied air supremacy. This supremacy resulted from many factors, including the long range of the P-51 Mustang, excellent American pilot training, and overwhelming Allied numerical superiority. However, the petroleum engineering advantage provided by 150-grade fuel played a significant role. The purple-dyed gasoline transformed good fighters into exceptional ones, gave Allied pilots confidence, and represented the technological and industrial might of nations capable of outproducing, out-innovating, and ultimately outlasting their opponents. Speed matters in aerial combat. A faster fighter can choose when to engage and when to escape. A faster fighter has the tactical flexibility that slower opponents lack. As American fighters became demonstrably faster through superior airframe, design, and 150-grade fuel, the Luftwaffe's tactical options narrowed sharply. The contrast between German and Allied situations in late 1944 and early 1945 was stark. Allied fighters could fly multiple combat missions daily, limited only by pilot fatigue and aircraft maintenance. German fighters, by contrast, often sat grounded for lack of fuel. When they did fly, they operated under strict fuel conservation measures that severely limited their combat capability. A German pilot who burned too much fuel in combat might not have enough to return to base. Allied pilots, however, could use full power when necessary, confident that enough fuel remained for the return flight. This operational flexibility had strategic implications. Allied fighters could maintain standing patrols, react to threats aggressively, and sustain continuous operations. German fighters, on the other hand, had to pick their moments carefully, conserve fuel rigidly, and often break off combat, not because they were losing, but because they were running low on fuel. Luftwaffe pilots knew that every sortie might be their last. Not because they might be shot down, but because they might not have enough fuel for another mission. Allied pilots, by contrast, flew with confidence stemming from material superiority. They knew their aircraft were fast, their fuel was plentiful, and their support system was robust. This confidence translated into more aggressive tactics, better combat results, and higher survival rates. The story of 150-grade fuel is a story of industrial warfare. Victory went to the side that could produce not just more aircraft, but better performing ones. Not just adequate fuel, but superior fuel. Not just enough trained pilots, but an overwhelming surplus of well-trained pilots, backed by an industrial base capable of replacing losses faster than the enemy could inflict them. American and British fuel chemists working in laboratories and refineries never flew combat missions over Germany. They never faced flak or enemy fighters, but their work, measured in performance numbers and manifold pressure readings, helped decide who controlled the skies over Europe in 1944 and 1945. Every time a P-51 pilot pushed his throttle forward and felt his Mustang surge ahead with power that German fighters could not match, he was benefiting from chemical engineering that transformed crude oil into a fuel that made the exceptional routine. German planners had assumed American fighters would perform within predictable parameters based on aircraft design and standard fuel capabilities. What they encountered instead were fighters whose performance exceeded their calculations, sustained by a fuel production infrastructure so vast and sophisticated that it represented industrial capacity Germany could not counter. By the spring of 1945, as Allied armies advanced from the east and west, the Luftwaffe had effectively ceased to exist as a coherent fighting force. A few units still flew, often with barely enough fuel for a single sortie. Jet fighters like the Me-262 represented a technological leap forward, but they came too late and in too few numbers, handicapped by fuel shortages and the absence of experienced pilots who had been systematically destroyed in combat. The final tally shows the cumulative effect of Allied advantages. American P-51 groups across all theaters flew hundreds of thousands of sorties, claiming approximately 4,150 enemy aircraft destroyed in air combat and another 4,131 destroyed on the ground. These numbers represented not just aircraft destroyed, but pilots killed, experience lost, and German industrial capacity wasted building replacements that were destroyed before they could achieve strategic impact. 150-grade fuel wasn't solely responsible for this outcome, but it was a significant contributing factor. It represented the margin of superiority that made the difference between a close fight and a decisive victory. The 448 mph properly boosted P-51 could achieve represented not just velocity, but technological superiority and industrial capacity. This was what German planners had not anticipated, that American fuel chemists and petroleum engineers, working far from the battlefield, could create a weapon as effective as any gun or bomb. That purple-dyed gasoline could influence aerial combat just as much as superior tactics or better training. The key to air supremacy over Europe in 1945 lay in the compression ratios of piston engines, the anti-knock properties of aromatic hydrocarbons, and the performance numbers of aviation fuels that exceeded anything Germany could produce. The P-51 Mustangs that flew over Berlin in early 1944 were remarkable aircraft. The P-51 Mustangs that flew over Berlin in early 1945 were the same aircraft, but they were powered by fuel that made them faster, more powerful, and more effective. That difference, measured in octane numbers, performance ratings, manifold pressure readings, and airspeed indicators, was one of the many factors that decided who would win the war for Europe's skies. In that decision lay the fate of Nazi Germany and the demonstration of Allied industrial might, expressed as a purple liquid pumped into fuel tanks, burned in powerful engines, and transformed into victory one combat mission at a time.